So again, that equilibrium reaction statement and constant that you saw, we're going to be working with it more later on and doing more math and calculations. But however, we are going to, but we're not going to focus on that today. Or this week. So we saw the overall reaction when the acid dissolves in water. However, how I was mentioning towards the end of the video, even though I cut it off a little bit short, we are assuming that our water and our H3O plus ion, that the concentration of water essentially stays the same or remains constant when the acid is dissolved. Because we're assuming that the concentration of water of H2O is constant, we can remove the H2O and we can remove the H3O plus to have a much simpler reaction per se. So I'm going to call this the acid dissociation. The thing stopped. Acid dissociation or ionization reaction, which I label as RXN. Okay. So our reaction, if we're going to remove the H2O and the H3O plus, because we're assuming the concentration is the same, we're going to have HA in aqueous form. We have our double arrows. However, in the practice that you'll have in the Google Doc, I had to use double-ended arrow because I wasn't able to input this one. H plus aqueous plus A minus aqueous. Okay. So let's do some examples. Today you're just going to be identifying the acid, the base, the conjugate acid, the conjugate base, and writing these acid dissociation reactions based off the chemical or compound that you're given. Okay, I don't know why that stopped. So example 1. So example 1, we're going to have hydrochloric acid. Okay, which is HCl. So if we have HCl, right, we're going to start off here. It has our H, and then our Cl is our element. So HCl, that's what we're starting off with. So HCl, and nothing changes, it's in aqueous form. Okay. Our H plus is always going to be there. So whenever you were doing stoichiometry, and things like that, right? You probably remember that we had like 1 mole or 1 of this. This guy here, not the best color. This guy here stays the same. Okay? The H plus is going to stay the same. It's going to be there. Why? Because remember, when we're putting an acid in water and it's dissociating and it's coming apart, we're taking that hydrogen, that proton, away from whatever element it's stuck to. Okay, so in this case we have hydrogen and chlorine. We're going to have our hydrogen by itself, aqueous, and you know what, let me do it in black because it stays the same. So H plus aqueous, and this one stays the same as well, plus A minus, so whatever element was with our acid, which in this case is chlorine, it's going to be negative and it's aqueous. Example 2. Acetic acid, which you worked with before, right? Vinegar. And it's HC2H3O2. You might be asking yourself, well, in this case, right, you're going to have other examples and problems where you have 2 hydrogens. We have a hydrogen here, and we have 3 hydrogens here. And you might ask yourself, well, how do we know which hydrogen we're taking from? If there's a hydrogen in the front, like there is here, we're going to take that H, that hydrogen, that proton. If there was no hydrogen here and there's hydrogen on the end, or this one, we take from that one. But you always want to take from the one at the beginning. If there is one, if not, then you find which one to take from the end. If there's none in the end, then of course it's the one in the middle. So again, we're starting off with our acid, okay? So HC2, you're just rewriting the acid that you're given, okay? It's aqueous. We have our double arrow showing that it's reversible and at equilibrium. H plus aqueous. And then once we take off that hydrogen, if we're going to take off that hydrogen, in this case this one, what do we have left? We have C2H3O2 negative AQ. I don't think I actually talked about this or mentioned this, but the reason why we have these positives and negatives, like this one and this one, is we took the hydrogen away, so it has an extra electron, right? And then here we took off our hydrogen, which it was, if we look at the charge here, it was neutral, right? We took off the hydrogen, so now it has an extra electron. That's why it's negative, okay? You don't have to go down a rabbit hole. That's just how it is. Example 3, let's do ammonium ion, which is NH4 plus. These should be on the back of your periodic table in the polyatomic ion, chart. So NH4 plus, if it dissociates in water, that's what we're starting off with. NH4 plus, it's an aqueous form, double arrow. We still have our H plus and aqueous. And then we have what's left. If we take away a hydrogen here, in this case, that's only hydrogens that we have. If we take a hydrogen there, what do we have left? NH3, aqueous. Here you have to be a little careful because our acid was positive. We took the hydrogen. If it was positive, it stays neutral. There's no charge here, okay? If we didn't have the positive and it was just NH4, this would have been NH3 negative. But because it's positive, it's incoming positive. And we're taking away one, right? It's like if you had $1 and you take away that dollar, you're at zero. You're balanced. So we don't need a charge here. So just be careful with that. This H plus is still positive. Why? Because when we take away a hydrogen, the hydrogen is positive. And last example 4. Example 4, let's do anilinium ion. Oh my goodness. I don't know why it does that. It's annoying. Ion. C6H5 NH3 plus. So again, starting off with the acid that we're given, we have C6H5 NH3 plus. It's an aqueous form. We have our double arrows. Oh, those are not great arrows. I'm sure yours will look much better. We have our H plus aqueous. That doesn't change. Plus. And then now what do we have left over? Again, if we look, we have 2 hydrogens, right? Again, you take the hydrogen from the front, then from the back, and then if there's none, you take it from the middle. Why? Because if you think about it, think about when we were drawing 3D 3D models for the different chemicals that we have, it's easier to take away electrons or elements, hydrogens in this case, from the ones that are on the very ends. Because if they're towards the middle, that means that there's more charge and electronegativity. Think about a magnet. The ones that are in the middle are more strongly, tightly bonded and held, so it's a lot harder to take it away. So that's why you want to take away from the ends, and then you would have to go towards the middle if needed. But typically you will have one at the beginning or the end to take away. So what do we have left over? We have C6H5 NH2. Again, there's no negative charge here because we started off with the positive. So let me write that here. Positive charge, or start with positive charge. Neutral conjugate base. So lastly, what I want us to do, because you're going to have this in your practice, and we didn't do an example that was exactly like that. So let's label them. Where do we have our conjugate acid, conjugate base, acid and base? So in this case, right, if we're looking at this example number 4, the one we're starting off with is our acid. Although it doesn't have the hydrogen in the front, it still is our acid, okay, because we have these hydrogens in the end. Our base, it doesn't show up, but remember, our base is going to be our water, okay? Our base is going to be our water. We took it out of this equation, although in your practice you will have water in it. We took it out. Why? Because we assume that the concentration stays the same. I'm repeating that a lot because you might see that on upcoming quiz. Not this week, next week. Okay, and then we have left our conjugate acid and conjugate base. Our conjugate acid is what is formed when the proton is transferred. So it's going to have to be this one. Our conjugate base is what is left over when we get rid of that proton, of that hydrogen, which is going to be this one. Okay, that is it. I know the notes were pretty long today, but it was mostly me talking. And you'll have your practice on this stuff. Hopefully you find it easy. We'll jump into math next week. Have a great day.